Assalamu alaikum, myself Ahsan Siddiq. My registration number is 23TE3. Today we are working on the assignment 2 of artificial intelligence, in which we will discuss about the logical agents and the propositional logic along with the forward chaining, backward chaining, first order logic and inference in first order logic. Our first topic is logical agents. A logical agent is an intelligent system that uses knowledge and logical reasoning to make decisions and solve the problems. Instead of acting randomly, it stores the facts about the environment in a knowledge base and applies logical rules to infer the new information. So basically, in logical agent, we have some facts and we have some knowledge. We use that knowledge in order to solve some problems. Instead of acting randomly, what we do is we try to perceive the environment, and in accordance to that situation we work on it. So the main component is you have the information, you have the facts. The second is that you will apply those facts in order to perceive something from the environment, and then you will make a decision according to that. So the general structure is that you have the environment, you apply sensing on it according to your knowledge, you get an inference, you make an inference, and then you make a decision or action. For example, if we have a smart campus security robot, and this robot is working, like if the motion is detected at night, the alarm will be generated. So we can have the facts like if the motion is detected at night, an alert should be generated. The next fact could be like motion is detected and it's night. So the propositions, let M is representing motion detected, N is representing the night time, A is representing the alarm generated. So we can make a no, like make a mathematical form in this way. So if M and N are true, which implies A is true. M is representing like if the motion has been detected and it was night, so it implies A means like alarm will be generated on that situation. So we can see here that if M and N both are true, like we are the motion has been detected and it is the night, the alarm will get generated on this record, on this situation. So we have concluded in this assignment that how we can train our agents to have to draw some facts and work on it based on the situation. The next example is autonomous greenhouse agent. In this, for example, we are making a system that will decide like when you will have to water them. Okay, so the proposition is D is soil is dirty, dry, H is temperature is high, and W is water pump on. So we are making a situation like if the soil is dry and we have a high temperature, so the machine should be able to detect those things, and water pump should get on. So we can define this by this, like if D and this is representing AND operator and H are true, which implies W is true. So this is how we can set up our environment in order to communicate the idea that what we have to do, that what our agent has to do on this situation. The next topic is proportional logic resolution. In this topic, resolution is a proof technique used in artificial intelligence and logic to determine whether conclusion logically follows from a set of premises. It works by repeatedly combining clauses to eliminate the opposite literals. So in this proportional logic, we have some proofs in artificial intelligence, and we use the logic to determine like the things we are trying to convey or we are to do are working logically or not. For example, like if A and B, if we have A and B, and we have minus of A, minus not of A, or C, then the resultant will be B or C, because A and minus A will get cancelled. Like if you see the general structure, so you can see here A and B, not of A over A, B can get resolved into B or C. So let us see the example of this. Means the student is present, and Q means the student will can take the quiz. So rule we have settled is like if the student is present, he can get the quiz. Okay, so in using a modus ponens rule, we can say like if P is true, which implies Q is true, like if the student is present, then the he can take the quiz. So this is how we have seen that we can set up this environment of our AI agent that will work on a logic like if the student is present, only he can then give the exam or whatever the quiz they are giving. We can have real life interpretation as well, like for example, suppose Ahmed comes to class today. If Ahmed is present, the rule says he can take the quiz, otherwise he cannot take the quiz. So the main comparison between these two ways make it the logical agent makes the intelligent decisions and resolution prove logical conclusions. The main difference is in resolution, propositional resolution, we try to prove our logical conclusions that we have done for a system, but in logical agents we make intelligent systems. So they are very far different from each other based on their perspective. If we talk about the uses, it logical agents is used in AI systems, and resolution is used in automated theorem proving, knowledge form, facts and rules, and it works on clauses, CNF, and output is action decision and proof of conclusion. Like in one thing, we are using the rules and facts in order to get some questions or some problems to get solved, and in the other one we are proving our conclusion that we have applied a right conclusion or not. We have explained the examples as well. So this is all from these two topics. Now we will move on to the next topic, which is forward chaining. So what is forward chaining? Forward chaining is a data driven inference technique that is used in artificial intelligence. It starts with the non facts and repeatedly applies inference rules to derive new facts until the goal is reached. So in this forward chaining, we have the certain available facts. We use those facts in order to drive the new rules, and those rules help us to get to our destination. So the procedure is very simple. We are given with the available facts. We try to make the new rules by using those facts, and then new rules are generated, and then we are moving, like we continue the same process until our goal is reached. For example, the available facts for a given example is A equals true and B is true. Okay, and the rules are like R1, in which A and B implies C, which means like if A and B will be true, it means C is true. And if C is true, the D will be true, and if D is true, it means E is true. So we can see this example here. It's a graph, and what we need to where we will gonna start, we will start from the fact which is given like A and B are true. Okay, so if we see the rule 1 that says A and B are true, it means this condition of AND operation is satisfied. Both A and B are true, it means C will be also true. Therefore C is our next, we have satisfied the rule and C is our answer. In step 2, C satisfies R2 because C implies D. It means that if C is true, the D will be true. Okay, and in the third step, we can see D is satisfying R3 because D implies E. Means if D is true, then E will be true, and D is our goal state as shown in the example. So what we have done, we have used A and B. We have the fact that A and B are true. So their imply means their and results in a true thing, obviously, and that has resulted implies on C. And if C is true, it means D is true, and D is true means E is true. So this is was the example on our forward chaining. The next topic is backward chaining. It is a goal-driven inference technique. It starts with the desired goal and works backward to determine which facts must be true for the goal to hold. Okay, now in this process, we start backwards. Like we have the goal, we use that goal to make the rules, and those rules helps us to get to the original state or the initial state. It means we are moving backward by the name of it. If you see the example, same example in which the rule 1 was A and B results in implies to C, and C implies D, D implies E. Our goal state is E. So we will start working by the concept of backward chaining from E. In order to get the E, it means that D was true because D implies E. It means that if E was like we have got the E as our final state, it means D was true. Similarly, if D was true, then C would have been true. Otherwise, we would not have D as our answer. And similarly, if C was true, then it means A and B both are true because their AND operation is true. Okay, so we have seen that how we are moving from a goal state, we are satisfying the rules, and we are getting to our original state. So we can see the procedure here, step by step solution as well. The goal was E. To prove E, use D, implies E, and we need to prove D, we can use C to D, and in order to prove C, we have the rule that A and product B and then C. So available facts that we got after the this process is A is true and B is true. Otherwise, C would not have been true. So in this way, we have done working on backward chaining. Now the next concept is first order logic. First order logic is a knowledge representation language that allows reasoning about objects, properties, and relationship using predicates and quantifiers. Predicates means the relation with any object. Like for example, I'm a student, so my name is Ahsan, and student is my relation, like I'm a student. Similarly, if there is a car, so that car it's a BMW, so the predicate will be car. And similarly, quantifiers are mathematical signs that are used to represent something. So the components of first order logic is constant, that can be Ali, Ahmed, Yasin, anyone. Variables could be x and y, predicate the relation, and the function is like father. Quantifiers are these two quantifiers. This one is called as universal quantifier, that means for all things. Like if we are going to include everything, we will use this symbol. And this one is representing essential quantifier, means like there exists. Okay, so we can take those examples as well. Like for all students implies intelligent. Like if you are a student, then you will be intelligent. An essential quantifier example would be for example, if you are writing this symbol along with the student, it means that some students are existing in the class. Now if we talk about the numerical example in the first order logic, so that could be, we can apply like for all human implies mortal. Like if you are a human, then you will be mortal, you will be like you have will have a day of death. Similarly, we can uh, rule have can have a knowledge base. Human is a Socrates, like Socrates, or we can write any name here like Ali, Ahmed, Jamil, or anyone else. Okay, so in this representation we can see that the what were the rules. All humans are mortal. The fact is Socrates is human, therefore Socrates will be mortal. So you can say like uh, we have done, by the definition, we have the relation, we have the reasoning about the objects. So we have concluded that you like all humans are mortal, and Ali is a human, so definitely he will be mortal as well. We have used this knowledge in order to get the conclusion sentence. Now, the next thing is our inference in first order logic. Inference in first order logic is the process of deriving new facts from the original ones. For example, and this is most common modus ponens rule is used in it. Like for example, if P implies Q, like if P is true, then Q will be true. Okay, and we can use this example in this way. Like what is the rule? Rule is that if for all students will get pass, and the fact is Ali is a student, so universal instantiation will be like replace X with Ali. Okay, we have written this here in which we have written student and X, and or Ahmed or any name we can have. Then we apply modus rule, in which if student Ali, it means pass Ali. Like first we have said if you are a student, you will, it implies to pass. Like if you are a student, you will get pass. Now Ali is a student, so he will get pass. Similarly, graphical representation can be shown in the next page properly. Like student was Ali, it implies that Ali will get pass, and pass Ali will be our final answer. So we have used the concept of inference logic in order to get the final answer. We had the existing rule in which we had said that I'm giving the explanation of this whole numerical example in a way. Like first we have seen that if you are a student, it implies that you will get pass. Then we have seen that if Ali is a student, it means he will get pass. So the final conclusion is Ali will get pass in the exams. So the concept or the key difference between you can say like is that the forward chaining works on the facts and then moves to the goal state. Okay, backward chaining, you move from the goal and you came backward in the processes by using those roles in order to get the initial state. In first order logic, you see the objects relations, and you have your knowledge in order to get some decisions. And inference, you have the facts as well, and you have the rules as well to get the examples, and we have discussed all the examples as well. So this was the main difference between them. Forward chaining starts with the non-facts and drives the conclusion. Backward chaining starts from the goal and goes to the it sees for the supporting details and move on to the supporting facts. That is our initial state. In inference, in first order logic, a formal language for representing the knowledge, and inference in the mechanism used to derive new knowledge from the FL statements. So this was all from my side, from back training first order logic and inference in first order logic. Thank you so much.